dependent t-tests. We do this when we have one group that has been measured more than one time. Things like pre-test and post-test. We also use a dependent t-test when we are looking for statistical significance of this one group measured more than one time. And finally, we must have continuous level data, either at the ratio or interval levels, like test scores or weight gain, anything that has a continuous numerical value. If you were to look through your book, you'd see formulas like this to actually come up with your answers. Feel free to follow this. However, there are easier ways to do it. For example, physical education director claims by taking a special vitamin, a weightlifter can increase his strength. 8 athletes are selected and given a test of strength using the bench press. After 2 weeks of regular training, supplemented with a vitamin, they're tested again. Test the effectiveness of the vitamin regimen at alpha equals 0.05. Setting this up, our pre-test would be mu1. Our post-test, after the 2-week period is over, that would be mu2. We're hypothesizing that when you compare the pre to the post, that the post is bigger. First time you test, you take the vitamin, and then you go higher for increase of strength. So when we set up our hypothesis test, we're hypothesizing our research, hopefully going to show that mu1 is less than mu2, which means that with our null hypothesis, mathematical opposite, and always has the equal sign. Our alpha value is 0.05. The less than symbol in our research hypothesis is less than, inferring a one-tailed test. So on our printout, we'll read a one-tailed test. Let's go look at some data. Here are athletes with a numerical code to protect their identity of numbers 1 through 8. Here's their test of strength before, and here's the test of strength after. So it is one person measured 2 times. Another person measured 2 times, hence dependent on who took it. Our process for using Excel, if you don't want to use the formulas found in the book, though it is my expectation you read over them, go to Data, Data Analysis, scroll down to the bottom. Now we're going to look for a t-test, again because we only have 8 pieces of data, a small sample. But it's paired, one and another paired together. Paired to sample for means. Put in your first range and your second range. In this case, alpha is 0.05, so we're okay to go. And here's my printout. Because my test was one-tailed, I'm more concerned with the one-tail probability, 0.10. So I have cut and pasted in my probability value. Now let's compare them. Again, just as a brief refresher, let's look at this pictorially, drawing in the mean at the halfway mark. Alpha is 0.05. I'm looking at the less than values, so I'm going to be at the left, meaning all this area in here encompasses 5% of my curve. Where would 10% fall? Well, 10% is more than 5%, so 10% would take up a little bit more, such as right here. That would come from my calculated value, and you can see it is not in the rejection region. I would not reject the null. I would fail to reject the null. In short, what I thought was happening isn't. What I thought was going to give me some good vitamin sales might not. The interpretation in layman language, there is no statistically significant strength gain after taking this certain vitamin for 2 weeks. Students in a statistics class were asked to report the number of hours they slept on weeknights and weekends. At alpha equals 0.05, is there enough evidence to show a difference in the mean number of hours slept? We'll let the weeknights be represented by mu1. We'll let the weekends be represented by mu2. The word difference implies a not equal to tail. Let's set up our test. Mu1 does not equal mu2, which means mu1 equals mu2 if nothing changes. Alpha is 0.05. Again, we have a two-tailed test, and let's go get our printout. Here you see your data. Our data analysis shows a two-tailed probability of 0.03. Pictorially, our alpha of 5%, two-tailed, would look something like this, about 2.5% in each tail. Where is this 0.03? Well, half of it goes here. Half of the 3% would go here, and half would go here. It's in the rejection region. We will reject the null. But using the rule we have been using, is p less than alpha? If it is, we have significance. Well, our p-value of 0.03 and our alpha value of 0.05 less than is true. We're going to have statistical significance, in which case we will reject the null. We reject that nothing changed. We reject that they're equal, because now we have enough information to show in our interpretation there is a statistically significant difference in the number of hours slept on weeknights and weekends. In fact, back to our printout, looking at the mean number of hours, this was only a sample, but we can infer it to the population because of how far those numbers run from the mean. 6.7 on weeknights, 9.1 on weekends. Because of that information, I can now say students sleep statistically significantly more hours on the weekends than on the weeknights. Let's try another example. A dietitian wants to see if a person's cholesterol level will change if the diet is supplemented by a certain mineral. 6 subjects were tested. They took the mineral for a 6-week period. Can it be concluded that the cholesterol level has changed? Willing to be wrong 5% of the time? In other words, alpha. As before, we'll let the pre-test represent mu1, and the post-test will represent mu2. And we think that it's going to be changed. Does it say up or down? No. It says not the same. So my hypothesis, my research hypothesis, is that mu1 is not the same as mu2, which would mean my null hypothesis, they are the same, mathematical opposites. Alpha was 0.05, and because we have this unequal sign, we're dealing with a two-tailed test. When we go to our printout, one subject each measured before and after taking this certain mineral to check the cholesterol level. Dependent t-test. Data analysis. Scroll down to paired 2 samples and input your information. Alpha is correct at 0.05, and there's my printout. I had a two-tailed test, so in this case, I am concerned with the p-value for that two-tailed test, 0.168771. And remember, the rule says, if your p-value is less than alpha, there is statistical significance. So what about ours? Our p-value is 0.17 rounded. Alpha is 0.05. sign that would go there is greater than. If it's greater than, we do not have significance. It would be outside the rejection region. Again, if it's outside the rejection region, we fail to reject. What we thought was happening with this mineral, lowering cholesterol, didn't happen. It stayed the same. Any changes that we saw were only by chance. So our interpretation: last example. A reporter hypothesizes that the average assessed values of land in a large city have increased during a 5-year period. A random sample of wards is selected and the data in millions of dollars are shown. At alpha equals 0.05, can it be concluded that the average taxable assessed values have changed? Let's say we have an early assessed value. We'll represent that by mu1, and a later assessed value, and we'll say that's mu2. We have the word increased. Mu1 compared to mu2. If it increases, mu2 is bigger. If mu2 is bigger, mu1 is smaller. So the symbol there would be less than. In our hypothesis test, mathematical opposite, mu1 greater than, always has the equal in the null hypothesis. Mu2, meaning nothing has changed. Alpha is 0.05. I have a direction. Think an arrow. That arrow determines that we only have one direction or one tail. So when I go to my printout, I'm looking at the one-tailed value. Here's my data. The ward letters. Tax assessed in the first round. Tax assessed 5 years later. We go to data, data analysis, and we pick up the paired t-test. And our results show that on a one-tailed test, the probability that that happened by chance is only 0.001. It's pretty small. So when we use our rule, our p-value, we never actually say 0 because there's always an infinitesimal small chance. So go ahead and mark that 1. Is it less than 0.05? Yes, it is. If alpha, right here, would be 0.05, that would be determine my cutoff for rejecting the null or not rejecting the null. But when I actually do a calculated value, we come up with something really, really small, definitely in the rejection region. Definitely need to reject. Reject what? Reject the null. What we're hypothesizing is happening, we now have evidence to demonstrate. In our interpretation, we might say that there is statistically significant evidence to show the assessed values have increased in the last 5 years.